In this video, we are going to do an example involving projectile motion. So anytime that an object is launched into the air with a given velocity and launch angle, so there's some object, I'm launching it into the air with some velocity and some angle, the path that the object travels is determined almost exclusively by the force of gravity. So as you launch this object in the air, it's going to follow some path, and then eventually gravity is going to pull it back down until it hits the ground. It turns out that we can use vector-valued functions in order to completely determine the path traveled. So let's do an example, which says that an object is launched at a 60-degree angle relative to the horizontal. So that means this angle here, relative to that horizontal, 60 degrees up is the angle at which we launch it, at 49 meters per second. Okay, how far away does the object land? So it's telling me this launch speed, and it's asking how far away does the object land. It also tells me, remember, the acceleration due to gravity is 9.8 meters per second squared, and that gravity is accelerating the object downward. Okay, so we start problems like this by drawing a picture. So what should I draw? I can draw, the launch spot of the object. The launch spot of the object. So maybe I'll draw a dot here. Maybe this is from the spot from where the object is launched. Ooh, I missed the L in launch. So launch spot. Okay, and then I'll draw that horizontal for the ground. I'll draw the horizontal for the ground. And then this object is going to get launched. It's going to get launched at this angle. So as we do that, it's going to fly up in the air, it's going to curve, and eventually it's going to hit the ground again. So I'll extend this a little further. Somewhere down the road, it's the spot where it lands. All right, so what else does this tell me? It tells me that this launch angle is 60 degrees. And what that represents is, from this initial spot, if I were to draw just a straight line kind of in the direction at which it was launched, in other words, a tangent line, and then I draw the angle from that horizontal to the tangent line, that is a 60-degree angle. Okay, so part of what we do in problems like this, once we have this picture, is we draw axes. We draw some axes, x and y axes, and we define our variables. Define our variables. Okay, so I think it kind of makes sense to have this ground be the x-axis. So I'll have this be the x-axis. I'll put the origin at this spot it was launched. So then the y-axis I'll make vertically from that launch spot. That's not the only way that I could have done it. Like if I wanted to move the origin to some other spot, I could have. Often it kind of just depends on the situation in the picture. Okay, but I think this makes a natural choice here. So what variables should we introduce? Well, I know that there's time. So let's talk about time. So maybe I can let that be t. T is going to be the number of seconds. Number of seconds after launch. After this object is launched. Okay. And, one thing maybe that the problem didn't explicitly specify, which let me just go ahead and clarify, is I meant for this object to be launched from a spot on the ground. Technically, it doesn't say that. So technically, maybe this object was launched from somewhere in the air. Or maybe there was like a bunker and it was launched from some spot underneath the typical ground level. But I don't mean for that. I mean for it to be launched right at the ground level. Okay. So after we have this, now what we do is we make a list of all the things that were given in the problem, and then what is it that we want to find? So what I want to find is how far away does the object land? So that's something about position. I want to know, I'll put a bullet point, the final position. How far away does it land? Specifically, I want to know the distance from where it started to where it landed. I want that distance, that position. Okay, so what is it that we're given? Well, it tells me the acceleration due to gravity. So the acceleration due to gravity, I can represent that with the vector for acceleration. And I'm going to put this in my brackets notation. that acceleration is just purely downwards, so there's no x component. That's going to be 0. And then the y component's negative because it's downwards, 9.8. The other reason I know it's negative is the way I set up my axes, I made the positive direction be up, which means because acceleration is pointing down, that would be the negative direction. If I had set up my axes so that the y-axis was pointing downwards, then my y component here would have been positive. Okay, so I have this. I'll put a bullet point next to it. What else am I given? I'm given this initial launch speed. So I'm given the launch speed. That's the initial speed. So the way I write that is it's the magnitude of the initial velocity, v of 0. And I'm given that that is 49. Okay, and there's one other thing that I'm given, which is I know where it is initially. I know that initial position. So I'll put a bullet point. That is r of 0. And I know that initially it's at the origin. That's 0, 0. That's my initial position. So that's my initial speed. I'm also now given the initial position. Initial position. Okay. So one of the things I can do now to break down this initial speed is let's draw a picture. Let us draw a picture. So the initial launch angle, something like this. And I know that so I'm going to call this the initial velocity vector, v of 0. The magnitude represents its length. So I know the length of this vector is 49. I'd like to eventually be able to say what the vector is and rather than just its length, its magnitude. So I'd like to know what the components are. So if I break this up into its x component and its y component, I'd like to know what those are. So this is where angles can come in. I was told this is a 60-degree angle, and because this one's a right angle, the other one's got to be 30. And to get the other sides, I can either remember my 30, 60, 90 stuff from geometry class, or I can use trig. Because for example, if I did sine of the 60 degrees, remember sine is opposite over hypotenuse. So let me call the opposite side y, and then the hypotenuse is 49. So if I solve for y, the y value is going to be 49 times sine of 60. And then if I use my knowledge of trig, I know sine of 60 is root 3 over 2. So I get 49 root 3 over 2. If I do the same thing for this length here, I would have to use cosine of 60 rather than sine of 60. So I'll get 49 times cosine of 60. And cosine of 60 is 1/2. So I get 49 over 2. Okay, and now I have enough to write down my velocity vector. So v of 0, the x component, it's pointing to the right, which means it's positive. That's 49 over 2. And the y component's going up, so that's also positive. So comma 49 root 3 over 2. Awesome, my velocity vector. So I'm given the acceleration vector. Let's take its antiderivative to get velocity. So let's start doing some calculations at this point. Okay, so let me separate out the stuff what I was given and what I want to find. Let's do our calculations. So now taking my acceleration, let's do the antiderivative to get velocity. My velocity, well, the antiderivative of 0 is just going to be a constant. So let me call that c1. And then comma, I'll get negative 9.8 t plus a constant, which I'll call c2. So my velocity looks like this. Let's solve for those constants using this initial condition. So I can now solve for the C1 and C2 by plugging in. By plugging in our value for t, which is 0. Okay, so doing that, I get my velocity. When I plug 0 in, I get C1, and then comma, this becomes 0, and then plus C2. C1 comma C2. Okay, so that should match this initial velocity vector. So these x components should match, and these y components should match. So matching them, I get that C1 is 49 over 2, and that C2 is 49 root 3 over 2. So I can go ahead and write those back into my velocity vector. So v of t equals, C1 is 49 over 2, comma, I get negative 9.8 t plus that second constant, 49 root 3 over 2. Okay, so we are halfway there. We got velocity. Got to do the antiderivative one more time to get position. So my position function, r of t, let's do the antiderivative of this velocity. So the antiderivative of a constant is, it's that constant times t, 49 over 2 times t. I need a constant because I'm doing this antiderivative, so I'll get plus c3, comma, for this negative 9.8 times t, I do my reverse power rule. I add 1 to the power, which gives me a 2 up there, and then I have to divide by that power, divide by 2. So negative 9.8 divided by 2 is negative 4.9, and then I'll get t squared. And then this constant, its antiderivative gives me that constant times t, 49 root 3 over 2 times t. And then I need that extra constant that pops out, c4. All right, so we have this. Now let's use this initial position condition by plugging in t equals 0. So again, let's plug in t equals 0. That'll let me solve for these constants. So r of 0, if I plug 0 into this first component just becomes c3. The second component just becomes c4, because both of these first two terms become 0 if I plug in 0. All right, and now, matching these components, this x component has to match that x component, and this y component has to match that y component. So that tells me that both c3 equals 0 and c4 equals 0. Okay, awesome. So I'm ready to write down my position function. My position, r of t, is 49 over 2t. That constant is just 0, so I don't need to write it, comma, negative 4.9 t squared plus 49 root 3 over 2 times t plus 0, so I don't have to write that. So I got my position function. Okay, so what does the problem then tell me? Like, what am I trying to find? I'm trying to find this final position, which means that position when it lands. So what do I know about what it lands? Is there something I can use? Like, what should I do next, essentially, with this position to take advantage of, okay, I'm looking for this point when it lands. I want to have you do a quick pause for about 1 minute to see if you can think about, what do I do next? Pause it in 3, 2, 1, pause it. Okay, so hopefully you did that. Hopefully you paused it to think about that. So the key thing is, at this moment when the object lands, I know the y component of position. The y component is 0. So we know that when the object lands, the y component, this whole thing, which I call y of t, that y component of position equals 0. So let's just set it equal to 0. I can rewrite this as a fraction, so that'll be negative 49 over 10 t squared. And then I get plus 49 root 3 over 2 times t. Let's set that whole thing equal to 0. So I can solve this. I'm running out of room, so let's move it up here. Okay, so I can factor out, let's see, a 49. I can also factor out a 10 from the denominator. And then I can also factor out a t. So if I do that from the first term, I'm left over with a minus and then a t. From the next term, I'll get a plus, and then I'll get, I know there's a root 3 still. And the denominator used to be 2, but I factored out a 10 from the denominator, which leaves me with a 5 from the numerator. The way I can test that is, if I were to distribute this back in, this 5 is in the numerator, this 10 is in the denominator, they would cancel a little bit to leave me with a 1 up there, and to leave me with a 2 down in the denominator, which is what I have here. Okay, so I can factor out like this. this whole thing equals 0. So now, because it's factored, either this first part equals 0 or this second factor equals 0. So from this first factor, what makes that be 0? Well, it's if t is 0. From this second factor, it's if t is 5 root 3, and the units of t are in seconds. The other way I could have solved this is a quadratic equation, so I could have done the quadratic formula if I really wanted to, but because t was common to both of these terms, I think factoring was quicker. Okay, so there's 2 times. What does that mean in the context of the problem? Well, t equals 0, that would have been this initial time, this launch time. So that means the other value I got should be the landing time. So this 5 root 3, this is the landing time. And I'm trying to figure out how far away did the object land, which means I want this horizontal distance. I want the x value of position. So I now need to plug this in, plug into my x component. So plug it into the x component, I'll get x of, plug in 5 root 3, into this x component. That's going to give me 49 over 2 times 5 root 3, which if I multiply that out, 49 times 5 is 245. And then I'll get root 3 over 2. And there's units in the problem. The units of, so x is a length, are meters. And we got it. We got our answer. So that is how we can solve a problem like this using vectors. If you've taken physics before, you've likely done problems like this. Maybe not explicitly using this notation, but instead of thinking of your x component and y component separately, but it's equivalent to this. In our class, I want us to practice doing problems using this vector notation, because that is the thing that we are learning. So in terms of our goals, we've now finished the last goal for the section. So in the next video, we are going to move on to the next section.